now we have two different limits as definitions for e. And as I mentioned in another video, eventually we'll have enough calculus that we can demonstrate these are actually true instead of relying upon, graphical and numerical evidence. But we just don't have enough calculus yet. But the calculus that we do have, with some clever substitutions, at least one of these things is going to help us show that the derivative of e to the x is e to the x. We're going to try to show this. And there's a nice little graph there with some slopes of some tangent lines. We're going to show that e to the x is its own derivative. Let's come over here because we're going to need some writing space. Okay. And I'm going to use one of these two limits, so I'm going to keep those things up there, of course, and I'm going to say that f of x is equal to e to the x, and we're going to use the limit definition of the derivative in order to show that e to the x's derivative is e to the x, right? That's what we got to do. We got to go back to the definition, the limit as h goes to 0, and we're going to do a little difference quotient, like we do. X plus h minus f of x all over h, where my f of x is the e to the x business. So I'm going to have e to the x plus h, right? The x plus h is going to go in for the exponent, that's right there, minus e to the x over h. Okay. Well, I wonder what we get if we directly substitute in a 0. Well, if we plug in a 0 for h, that's going to be e to the x minus e to the x, which is, of course, 0 over 0. It's 0 over 0. It's an indeterminate form, which we have to fix. Ooh, speaking of indeterminate forms, I'm not sure that I addressed this particularly back here on the limits. If we did the same thing with this infinity here, plug in infinity, 1 over infinity is 0, so I just get 1 there. This is 1 to, here, let me actually even change this color. This is 1 to the infinite power. That's an indeterminate form as well. A lot of people are confused by that one because it's like 1 to the infinite. It doesn't even matter what it's 1, and it's being raised to anything, it's going to be 1. But remember that these are functions. Like this is just getting closer to the number 1, and this is getting closer to the number infinity. So it doesn't work exactly the same way. This could be anything. And as you can see, that this one's actually equal to e. And then likewise over here, if we plug in 0 here, that would be a 0. This is 1. And then 1 over 0 is going to infinity. Oh, look, it's the same exact one. It's 1 to the infinity power. It's that indeterminate form. And then this one, we're getting our friend 0 over 0, which we know so well. Okay, but all of the methods that we've learned to resolve this 0 over 0, like, say, factoring or rationalizing common denominator, none of it really works. Or does it? Let's see. What I'm going to do is I'm going to fix this. I'm going to use some algebra. This is we have e raised to a sum of powers. Do you remember where that came from? That came from, if you multiply with like bases, you add the exponents, right? It's that rule. So that's how I'm going to rewrite this. Limit as h goes to 0 of e to the x times e to the h. Right? Does that make sense? So if I multiply these two e's together, I'm going to add the two exponents, and that's what I would get. Minus e to the x, all of this over h. Remember I said factoring as one of the rules that we could use, or one of the strategies, and we can factor because we have a common factor of e to the x there. I'm going to pull it out. E to the x times e to the h minus 1, all of this over h. All right, well, did that help me any? Let's see. If I plug in a 0 here, e to the 0 is 1, minus 1 is 0, but I still have a 0 on the top, so no, I still haven't fixed it yet. All right, so I got to keep going, and you know what? I'm going to break this up as instead of a limit of products, how about a product of limits? Let's do that. So the limit as h goes to 0 of e to the x times the limit as h goes to 0 of e to the h minus 1. Well, make sure that's not an exponent because it's not. over h. And now, according to the limit laws, that's perfectly okay to do as long as both of these limits exist. And I really don't know if this one exists yet. I still have to keep doing the math. If, for example, we did the math on this and we saw that this thing did not exist, then this would be an invalid step. We'd have to come at and we'd have to mark it all out and start fresh. Hopefully it exists. Okay, anyway, let's look at this first part here. Notice that the variable for the limit is, whoops, come on. No, all right, it's red. The variable for the limit here is 0, but the variable on x is, let me try that again. The variable on the limit is h, and this one is x. So this h value doesn't even affect this. When I take the limit of e to the x as h approaches 0, it's just e to the x. Right? And then this is the part that we have to try to fix here. So the limit as h goes to 0, e to the h minus 1 over h. And just a reminder that this is f prime of x, right? All right, so look at what we have so far. I'm going to even highlight this. We have the derivative of f of x, which is e to the x. It's also equal to e to the x times something. And one way to write that is like this. F prime of x is equal to e to the x times something. Let's make that something, I don't know, k. Or, you know, if you prefer, how about like k times e to the x? So if I write it like that, then I can see that the derivative here is directly proportional to e to the x. Directly proportional just means that you multiply by some constant of proportionality. And what is that constant of proportionality? It's the value of this limit, whatever it turns out to be. So this is the part that we have to try to fix, okay? So let's just focus on that limit that's right there and see what the heck is going on. Should I change colors? I'm going to change back to blue. Let's just take the limit as h goes to 0 of e to the h minus 1 over h. You know what? This looks sort of familiar when it comes right down to it. What if I replace this? What if I did this? What if I did the limit, not replace it, but just rewrote it in a form that might look a little bit more familiar to you? So limit as x goes to 0 of e to the x minus e to the 0 over x minus 0. What is that? Isn't this the same thing? Because look, e to the 0 is 1. That's this 1 that's right there. And then, of course, x minus 0, that would just be this h that's right here. And this should look familiar because this is equal to the derivative of the f of x, e to the x function, at 0. It's the alternate form of the derivative. All right, so we've made a little bit of progress here, just kind of understanding what this thing is. So the constant of proportionality actually turns out to be just f prime of 0, whatever f prime of 0 is supposed to be. All right, so we still haven't found that limit yet. And here is where one of these limits is going to come in handy for the limit definition of e. We have the limit as x approaches infinity, or the limit as k approaches 0. Which one do you think we're going to use? Well, the one that makes sense is this bottom one here, because it's about values close to 0, not values close to infinity. That's not what we do whenever we take a limit. So in some kind of way, we are going to do a substitution, a very clever substitution with this one. So the way it is as, let's say, when we're taking really small values of k in this case, but h in our case, then this quantity here is going to start approaching e. So if I take all of these little k's and I replace them with my with my eraser with h's. This is the substitution that we're going to use for e in that limit. Okay, all right. So I'm going to take this e out, and I'm going to replace it with the limit that we just saw, or the value, because it's as h approaches 0. And as h approaches 0, then, or k in the original limit, then the value of e can be approximated with limit as h goes to 0. I'm going to take the e out and put 1 plus h, not k's, to the 1 over h power. So I just replaced my e with that limit value that's right there. So what color is that? I think it's like this color. It is not that color. That looks tacky, but we're going to live with it. All right. So all of that, I still have this h power that we have to raise it to the h minus 1, all of this over h. And now we're almost ready to fix it. I have no idea why I switched to this red color or pink or whatever it is. I'm going to switch back to blue. Okay, what happens with these exponents? This 1 over h raised to the h, that's h over h, which is 1. So just 1 plus h to the first power, which I'm not going to write, minus 1 over h. Oh my gosh, it's coming together, because now I can get out my cancellation crayon and get rid of those things. And this is equal to the limit as h goes to 0 of h over h. H divided by h is 1. So the limit is approaching 1. All right, just, we did this little substitution, and if you're having a little, reservation about it, understand that I have to do tricks in order to avoid using this thing we haven't learned about called L'Hopital's rule. And L'Hopital's rule depends upon derivatives and stuff, and we haven't gotten there just yet, so we have to do all of these substitutions. But still, it might be nice if we just say plug this thing into a graphing calculator so we can verify that that actually makes sense. The value of 1 that we got actually makes sense. So let's just make a new one here. And it was y is equal to, and then on top it's e to the, we'll use x, not e times x, come on, e raised to the second power, brilliant, to the x power, and then it was minus 1, all of that divided by x. Okay, and then we're specifically looking at what value? Let's zoom in right there. Well, look at that. Of course, it would have a point of discontinuity right there at 1, but I can see some graphical evidence to suggest that from the left side and the right side of that, it's actually definitely, absolutely approaching the number 1. Okay, so let's come back over here then. And make sure that you have something written down for the derivative of e to the x being equal to e to the x. It is its own derivative. It is unique in that way. It is the only function that is its own derivative. Any other exponential function, let's say we're saying 2 to the x, is almost its own derivative. It's going to be directly proportional to its derivative. Okay, so the cool thing about the fact that it is its own derivative, that means that the y value at every single point on the graph of e to the x is the slope of the graph at that particular point. All right, so what's e to the 0? Well, e to the 0 is 1, which means the slope here is also 1. Let's say that I go over here to, let's say this is the number 1 here. E to the first power is e, which means that right up here at this point, the slope of the graph at that point is just e to the first power. All right, so in the next couple videos, we'll actually put this derivative rule into practice.